Thank you everyone for coming. Before I start, I just want to take a moment to acknowledge the traditional owners of the lands where we're meeting and pay respect to their elders, both past and present. I also want to say just thanks everyone for coming. It's the last day of a really exciting conference. If you're anything like me, you're probably running a little bit out of steam at this point. I certainly am, so I really appreciate you making the effort to be here. So I want to talk today about vagueness, which is something I've been thinking about for way too long, and probability, which is something I've been thinking about hardly at all. I'm very, very new to thinking about probability. I'm kind of excited about learning more about probability. Been trying to get my head around various ways that probability has been applied to different sorts of issues. So treat this very much, this is very much like a logician who doesn't know anything about probability, kind of coming to understand probability and trying to apply it to something. And now, if you're a sort of formally technically minded philosopher, you probably hear that and you go like, sweet. And if you're not a formally or technically minded philosopher, you probably hear that and you go like, oh no, why did I get out of bed? Why am I not sleeping in? I will do my best to have something of interest to everyone, but you know, it is what it is. My main task here, at least as I understand it, is to kind of try to roll together three areas that I find fascinating and interesting and I think mutually inform each other. And these are on the one hand logic, on the one hand probability, and on the one hand experimental results, actual data about how people actually use language. That's something that I care deeply about, and I think it's very important to keep our theories of vagueness grounded in the real phenomena that they exhibit. So there's going to be like, there's going to be weird experimental stuff too. So there's like, there will be something for everyone to hate. Okay, so let's start by thinking about vagueness. The AAP is a long-standing organization, certainly. It's founded in 1922. I guess that has to count as long-standing. And long-standingness, as we would expect, is not the sort of thing that draws a very clean or sharp line, right? If you have a long-standing organization, it must have been long-standing an hour ago. Similarly, if an organization isn't already long-standing, then waiting an hour is just not going to suffice to make it long-standing. But then this means that since the AAP is long-standing now, it must have been long-standing an hour ago, right? It couldn't have become long-standing in the last hour. It takes longer than an hour to make the change from non-long-standing to long-standing. And so then it must have been long-standing an hour before that, an hour before that, and an hour before that. And of course, we can conclude that it was long-standing at its founding. We can conclude that it was the AAP was already long-standing at the time of the building of the Library at Alexandria. The AAP was already long-standing at the beginning of time, et cetera, et cetera. But it was only founded in 1922, right? I mean, it's long-standing, but like, come on. So something's gone wrong. That's the Sorites paradox. I take it it's familiar, you've encountered something like it before. I myself today anyway, am not going to be particularly focused on like the paradoxical reasoning and where do we break that argument and so on. That's not going to be my focus for today. My focus for today is going to be more just about our use of words like long-standing and the ways in which we use them to draw these sort of whatever vague boundaries are, right? They're all over the place. In fact, most of the categories we use, I think, are like this. They're sensitive to large differences for some value of large without being sensitive to small differences for some value of small. And large differences are just a bunch of small differences, so that's impossible. And so this creates a range of puzzles and issues and difficulties. The other kind of main area that I work in is also kind of paradox-driven, focused on semantic paradoxes or paradoxes of self-reference, things like this sentence is false, and what do you say about that? And like, get me at the pub, we can have good long conversations about that, but I'm just not going to mention it beyond this today. One thing about those kinds of paradoxes, though, they're easy to avoid, by which I don't mean they're easy to solve. I mean, like, just if you decide you don't care, they will never affect your life. And vagueness is not like that. Right? These issues around line drawing come up all the time, every time we use kind of all our most common words, anytime we're making judgments. You know, I mean, think how many times you need to resolve borderline cases just in marking an essay, and then think how many essays you mark every semester. Like, we're constantly grappling with vagueness. It's not avoidable in the way that some paradoxes are avoidable. And not only do we do it really well. We do it really fluently. We do not, in fact, have our practices massively disrupted by the fact that small differences don't matter and large differences do. That, to me, is really puzzling. Like, how do we pull off the trick? It's kind of hard to figure out what's going on. And this is, for me, this is a kind of motivation. So there's been, well, 75, I think of as kind of a place where the sort of logico-philosophical literature on vagueness really starts to take off and get rolling. So we've had a good solid 50 years of people coming up with really, really cool, weird logical systems for grappling with vagueness. I love that stuff. That's absolutely my bread and butter. I'm very glad that there's 50 years of literature there for me to dive into. And one thing that means is that although that, as you look back to the 70s and 80s and that starting literature, you see a lot of like, oh my goodness, how will we ever come up with a way to explain what's going on here? And it no longer really feels like that. Like, it's actually at this point, we just have an embarrassment of options. It's not hard to come up with a story. I mean, maybe it's hard individually to come up with each story, but standing on the shoulders of giants, we've got like 100 stories. And so for me, the question is more about filtering. Right? It's less about how do we get anything and more about, of all the massive range of options that we have, how do we figure out which of them actually has some connection to what we're actually doing? Right? We're presumably not doing all of the things the literature contains. So what sorts of tools can we use to figure out what we are actually doing? And so that's the way I want to approach it. It's not the way everyone approaches vagueness. It's an incredibly rich topic. There's lots and lots of angles that you can take into it. I don't want to say that, oh, people who aren't asking this question are doing it wrong. I'm just saying this is the way I'm coming in. My question is like, how do we actually deal with these categories? How do we actually deploy these categories in a way that avoids running us into the trouble that seems to be looming and lurking like just out of view all the time, right? But like somehow we manage to keep it out of view. We manage not to get screwed up by it. And yeah, I mentioned this earlier, right? There's also kind of something methodological going on here, right? I think logic and probability, I often think of as like metal and punk, basically, right? Like, or like metal and punk in the 80s, maybe, right? There's like these rivalries between them, but like to everyone else, they just look like they're exactly the same thing, right? But like, yeah, the people in these communities really care about the differences. And so, yeah, I don't know. I guess metal and punk have kind of, they're much cooler these days. There's much more kind of smearing in the middle. I'm trying to do something like that with logic and probability. And at the same time, I just like experimental stuff. I like staying grounded in evidence and seeing what people are actually doing. So, I don't know. This is how I like to do philosophy, and I hope other people like to do philosophy this way too. Okay. So that's our starting point. I'm going to start by thinking about what I and many others think is kind of obviously a bad idea. And I'm gonna, it's weird, right? Because one, it's obviously a bad idea. Two, in about 10 or 15 minutes, I'm gonna try to convince you that it's a bad idea. And so first I need to tell you a little bit about like, it's actually not as bad an idea as you might think at first, even though it's not gonna work. And this is a view that's out there, a range of views that are out there about these things. You can just deny the appearances and say, look, our categories just do draw sharp. Right? It doesn't seem that way, but surprisingly, they just do. There was indeed an instant at which the AAP suddenly leapt into longstandingness. Right? You just, at some point between 1922 and now, it was not longstanding, not longstanding, not longstanding, not longstanding, not longstanding. You turn away, you look back for a second, like, oh, it's already changed. Yeah, it's longstanding. Right? There's a sudden instant where that happened. This is the thing that I think, as I say, nobody is tempted by this view when they first hear it. But I think you can actually put some lipstick on it. So I like to think of this as the Matthew 5:37 theory of vagueness, right? Let your yes be yes and your no, no. For whatever is more than these is from the evil one. Or as they put it on the excellent source Bible.art, but let your yoli ye be ya'a yani manti then inatis. For whatever is more if these cometh eve of evil. Bible.art, by the way, is a phenomenal website. I just stumbled across it yesterday. It's incredible. It's serious. They're not taking the piss. Like it's genuinely, it's just AI slop, but it's like good, bad, funny AI slop like we used to get 7 or 8 years ago. Like, yeah, it's that. It's brilliant. Anyway, Or here in the sort of graph that I'm going to start to use to convey certain sorts of things, here's another way to think about this sharp lines view. So a way to read this sort of graph, and as I say, there will be a number of graphs like this. I want to read across the bottom, just thinking of those as like, how many years old is the AAP, right? Go from 0 to 100 years old. It's more than 100 years old now, but I'll just think about the first 100 years. And then vertically, in this case, we're thinking about the truth value of the claim that the AAP is longstanding. And as is customary, and as will turn out to be handy for certain reasons as we go on, I'll use 0 as the truth value false, 1 as the truth value true. And the idea here is just that there aren't any others. There's nothing else to do. So what must we have had? We must have had it be false for some amount of time. And then at some instant, I put it at 50 years, but like, whatever. At some instant, it suddenly leaps all the way to true, right? This is this sort of sharp line picture. And I think one important thing to remember about this, to understand the view, it's not intended to represent a chosen policy about our use of the word longstanding. Of course, we can choose that policy. We can say, for the purposes of a conversation, like, okay, in this conversation, when I say longstanding, I mean more than exactly 50 years old or whatever. Certainly we can do that, right? This view is not a view about that. It's meant to be an already existing fact that this word draws a sharp distinction. It doesn't need to be at exactly 50 years, but there is somewhere where it draws that sharp distinction. That's the nature of this view. Now, we definitely don't know where that sharp distinction is. And this is where this view starts to actually take on some of its plausibility. It tends to come with a package of views around vagueness and knowledge. Right, you say, okay, well, it seems implausible that there's any such thing, but if we don't know where it is, then maybe that can do something to explain the lack of any obvious sharp line. And we get something of a kind of multiplicity that can come out of this, right? Say, okay, sure, there's only one real sharp line. There's the one real instant at which the AAP became longstanding. But there are many sharp lines that, for all we know, are that real sharp line. Right, we don't know where the one is, and in fact, there's this wide range of options around where it could have been. So we're thinking to some extent about our knowledge, our ignorance, the range of possibilities, and ways we might have beliefs around them. And not when those sorts of views were starting to be developed and brought to the fore, but nowadays, when people are thinking about knowledge and ignorance and so on, credences, degrees of belief, things like that are very rarely far behind. And so I think it makes sense if we're going to think about this view where, okay, there's a sharp line, but we don't know where it is. Sure, we don't know where it is, but like some places seem more likely than others, right? I put the line at 50 years. That seems like maybe not a terrible option for an example. Certainly a better option than if I had put the line at 2 minutes or something, right? Like there are better and worse places to draw the line, and we might represent that in terms of ignorance by thinking in terms of degrees of belief. And the sort of two real precedents here for thinking about vagueness in these terms, at least the two that I look back to, are Emile Borel and Dorothy Edgington, both of whom, in different ways, developed this kind of probabilistic degree of belief, credency sort of story around these things in their own separate ways. Yeah. I mean, interestingly, Borel's doing it like actually around the time of the development of the probability calculus in the first place. Like this is a very early application of probability, is to vagueness. Edgington is coming along later and doing a slightly different thing. But anyway, these are like the two towering figures in probabilistic theories of vagueness, I think. So as I said, I'm pretty sure the sharp line at which the AAP became longstanding is not in 1800, 122 years before the AAP was founded. I'm pretty sure it was not even in 1925, 3 years after the AAP was founded, but it wasn't longstanding in 3 years. I'm pretty sure the sharp line wasn't 4 years ago. It was already longstanding then. I'm pretty sure it's not in the future. It's certainly already longstanding then. I don't think the sharp line was in 1950 when it was 28 years old, but that's maybe more plausible anyway than 1925. And was the sharp line somewhere in 1973? That maybe not. Like I feel much more uncertain about that. So I'm going to assume that degrees of belief can be represented reasonably as numbers from 0 to 1 inclusive, where 1 means you're totally certain of something, 0 means you totally reject it. 0.5 is halfway in between, and we do all the sort of various in-between sort of stuff. if you're familiar with degree of belief kind of thinking, no, I am not making any assumptions here about how these degrees of belief relate to like the probability calculus or axioms or whatever. That's part of what's at stake and part of what I want to be thinking about. I'm just assuming that we can represent degrees of belief in this way as numbers from 0 to 1. And I want to give you there's so many ways to think about probability. As I said, I'm kind of new to probability, so I'm really trying to get my head around all these different ways. Here's a way to think about probability that will be useful for what I'm going to do with it today. There's so many ways to think about probability, but here's one that you might find handy. I find it handy, and I'll be using it today. So I want to think about valuations from classical logic. I'm going to start thinking about classical probability. So we've got 1 and 0, and just two-valued binary logic. And I want to give an example of this. So take a flip of a fair coin, and we're going to have two atomic sentences, right? You let H be the claim that the flip came up heads, T be the claim that the flip comes up tails. It is important for some of the results I'm going to use that we only have finitely many atomic sentences. I'm not going to comment more than the comment I'm in the middle of right now about that restriction. There are places where it matters and places where it doesn't, and places where I'm not sure whether or not it matters. So I'm just going to assume throughout that we only have finitely many atomic sentences in our language because that makes things easier for me. You don't need to care about it, but if you do antecedently care about it, there's a thing you should know. Okay. With two atomic sentences, we have 4 valuations we can think about. Right? Each of those could be true or false. Each of those could be true or false. So we've got 4 possibilities, each of which is a row in this truth table. And we can think about more complex sentences. And again, I'm assuming a sort of classical approach for now to these more complex sentences. So we've got H or T. Well, that's going to be true. That's going to take the value 1, just in case at least one of H or T takes the value 1. So in those first 3 rows, that's true. 4th row, it's false. Or we can think about H and T, right? That the coin comes up heads and tails. That's going to be true only in the first valuation and not in the following 3. And now, if you know how coin flipping works, you might think, well, the coin can't come up heads and tails. Sure, totally, it can't. But like these are H and T, these are atomic sentences in classical logic. There's very much is a valuation that assigns 1 to them both. And the way you would represent your knowledge that things can't come up that way would be to assign that row a probability of 0, right? So in addition to having a normal truth table, I want to assign each row of that truth table a probability. Here's like a reasonable example, right? It is possible that the coin doesn't come up heads and doesn't come up tails. Maybe it gets swooped up by a passing ibis. Maybe it rolled under the refrigerator, and then under the refrigerator is like a pit of lava that dissolves. Or maybe it doesn't count as coming up heads if it rolls under the refrigerator, right? Even if it lands head side up. You might think, wait, no, that doesn't count as coming up heads. Anyway, there is some possibility in a flip of a fair coin that like something goes wrong and it doesn't get resolved. But I don't think there's much of a possibility of it coming up both ways. So you might assign 0 probability to the first row and then, roughly 50-50 to the normal rows and then some chance of it going wrong. The only important thing about these weights is that they total 1. And that's just, it's handy. So here's a way to think about classical probability, right? You start from some finite collection of atomic sentences. You consider all the possible ways you could assign truth values to them, where I don't mean possible like metaphysically possible, right? It coming up heads and tails is presumably not metaphysically possible. I just mean all the assignments of truth values to those. And then you weight those, right? You take 1 worth of weight and distribute it however you like across all the various sort of possibilities or all the various rows of the truth table. That gives you a way to think about probability in a sort of classical setting. To get from here to actually assigning probabilities to sentences, there's a method that you use. And I'm just going to walk through an example of this method. Obviously, the particular example doesn't much matter, but I think it's handy to see how the method works. We're again going to go row by row right down the line. So we're going to ask, okay, what's the probability, say, of H or T? Right, the probability that the coin comes up either heads or tails. We're going to go line by line, and on each line, we're going to take the truth value of that sentence on that line, H or T, which so far is always either 1 or 0. We multiply it by the probability that that line gets. And then we add up all the results. So in this case, we've got 4 things to do. First line, right, truth value is 1, probability is 0. So we get 1 times 0, that's 0. Second line, truth value is 1, probabilities roughly a half. Third line, it's the same. Fourth line, the truth value is 0, probability is positive now, that gets zeroed out. And so we say, okay, the probability that the coin comes up either heads or tails is the sum of all those things, in this case, 0.998. Right? So we get probabilities out of this just by considering for each line, what's the truth value? If it's true, we count it, because multiplying something by 1 doesn't change it. If it's false, we don't count it, because multiplying something by 0 is the same as throwing it out, if what we're going to do with the result is add it. So we're basically just counting up the rows and adding their probabilities together. That's the view. But I want to think through this multiplication part of how we get there, because we're not going to be sticking to just 0 and 1. So if you take someone's belief state to be represented by this kind of weighted truth table, here's a bit of jargon I'm going to use. This is a convex sum of valuations. All that means is it's a weighted sum, and the weights have to add up to 1. So convex sum just means the thing we just did. And then we can read off that person's degrees of belief in complex statements by using this kind of method. And this gives you a probabilistic way, or a way to think about degrees of belief and probability. And there's a lovely little characterization result that's useful in these ways. For finite languages, someone's belief state, B, where that's just a function from sentences to 0 and 1, it can be any function. Well, that is arrivable at in this way. That's one of the ones that you could have got to like this, if it meets certain conditions that we can specify just directly in terms of the belief value. Right? So you've got to believe some classical theorem and fully believe some classical theorem and fully disbelieve some classical contradiction. You've got to make sure that if an entailment holds classically, that's what that weird little plug thing means. If an entailment holds classically, then your belief in the premise is no higher than your belief in the conclusion. And then the bottom thing, right, your belief that at least one of them holds, you think, okay, well, that's the belief that one of them holds plus the belief that the other one of them holds. But oh no, in places where they both hold, we've just double counted. So we say, okay, my belief that one of them or the other holds plus my belief in the double county bit is the same as the sum on either side. That's can be handy in some ways. What does it tell us about vagueness? Well, for any number I, right, think pi as the claim the AAP was longstanding at the start of its ith hour of existence. That's a lot of hours. I'm obviously not going to list out these claims, certainly not going to make a truth table. That's very, very big. But these have some structure to them that enable them, we can make them a little bit more intelligible. So let's suppose that we're just going to assign probability 0 to any of these valuations that have the AAP like fluctuating in and out of longstandingness. Right? Let's suppose that the plausible ones are the ones where the AAP is not longstanding for a while and then becomes longstanding and then remains longstanding. Right? And that allows us to say, okay, we'll just assign 0 to any valuation that's not like that. And so the remaining valuations can essentially be summed up just by specifying an instant at which the AAP becomes longstanding. All of a sudden, this is still a sharp lines view, right? This is still, there's nothing but zeros and ones in the underlying valuations. If you care about symbols, that's what that says. And here, I think, is a nice way to picture the belief state of someone like that. So what's going on here? Again, across the bottom, we're looking at the years of the AAP's existence from 0 to 100. Now on the vertical, we're not looking at a truth value. We're looking at like a distribution over all of these valuations, all the different places you might draw the line. Right? And you say, okay, someone's belief state might be unsure about all those different places to draw the line. And in fact, for any particular place, they're probably really very confident that the line isn't there. Right? Because these places are so precise, it would be shocking if the line was there. But nonetheless, it's more likely to be roughly in the middle and less likely to be out to the sides. And I've just plugged in what's called a normal distribution here, basically because I don't have any better ideas, right? I think normal distribution, like, why not? It would be surprising if it wasn't normal, but it doesn't have to be. But like, let's just assume it is to make things simple. So here's a representation of someone's belief state about this vague predicate longstanding. Well, what would they think of all these claims? The claim that the AAP is longstanding at hour 100, or at hour 100,000, or at hour 500,000. Well, those claims, the probability they would assign to those claims would just be like the sum of all, like how likely is it that the threshold is somewhere below here? How likely is it that the threshold has already happened? And as time goes on and on, that gets more and more likely. It gets more and more likely very rapidly in the middle, where the threshold's more likely to be. What are the odds that the threshold is down here? Incredibly low. And so what are the odds that it's below here? Well, so this is all about approximately zero. But once we start getting into the real meaty bit, the probability rises rapidly. And then towards the top, we say, okay, well, wait a minute. Almost certainly we've already passed the threshold. I don't know where it was, but it's probably somewhere back there. And so we sort of level off around 1. Right, so this is the sort of prediction you get around people's beliefs in the claim the AAP is long-standing as we look across time, if we imagine an underlying sharp line, 0, 1, no funny business base, and some standard probability at the top. And here's some experimental results. This is not about people judging whether the AAP is long-standing. This is about people judging whether certain shades of color are red or blue or green in various cases. And the thing to pay attention to here is the dots, not the curves. I'm just grabbing an old graph, unfortunately. The curves are superimposed and fit to the dots, so you shouldn't be too convinced by the curves. But take a look at the dots and note that the curves don't fit them all that badly. Right, the relative sort of that characteristic S shape that we have of that cumulative probability distribution matches pretty well with some of the experimental results about people actually being walked through Sorites cases and asked to judge of each thing. Okay, well, is this one red? Is this one red? Is this one red? So that's not bad. It's all built on an underlying classical sharp line space. Speaker behavior does not draw anything like sharp lines, but it does look a fair bit like what we'd expect if we just do some probabilities over the sharp lines. And so the sharp line thing, which may have seemed just like a complete non-starter, if we bring in some relatively standard probability stuff, goes much better than you might think. Now, there's an issue of interpretation. I presented all that as about like uncertainty and knowledge and so on. And that was a presentational choice I made. Using probabilities does not require you to interpret the probabilities as about knowledge. And I think there are probably good reasons not to, right? So on this approach, if we knew which valuation was the right one, if we were maximally informed, we should be maximally opinionated. We should have only degrees of belief 1 or 0, and so on. You might think that, I think that's kind of bizarre. I don't think that's likely to be right, right? I think, we could know exactly how the world is and still appropriately feel uncertain about whether the AAP was or was not longstanding at a certain moment. And if you interpret this all epistemically, you can't get that result, but that's a matter of interpretation. And to make that point, you can go back to Burrell, who is one of the earliest I know of recommending this kind of probabilistic approach. Burrell says, I would like to try and show that one can give these questions, where these are questions related to the Sorites, a perfectly clear answer, provided one makes systematic use of the principles of probability. And he does, in fact, give a story something like the story I just gave, but it's not an epistemic one, right? He says the questions are badly put if one requires a yes or no answer. It's not that the answer is unknown, it's that that's a bad question if it requires a yes or no answer. The true answer is a coefficient of probability. Right, so this is not an epistemic reading of the probabilistic situation. And so Burrell, turns out, is from the evil one. And there we go. Edgington takes a similar approach in her application of the formalism of probabilities to vagueness. Says, I do not say that the indeterminacy of vague concepts is an epistemic matter. There are different applications of probabilistic structure. And she gives some examples. Objective chances apply if and when the future is physically undetermined by the past. That needn't be epistemic. Relative frequencies also satisfy the principles of probability. That's not epistemic. I propose that it's also the right structure for theorizing about the indeterminacy of the application of vague concepts. So you can do this probability stuff without the kind of epistemic framing. I was just using that as a way to kind of get into it and make it sort of intelligible. But the formalism is up for being interpreted in many different ways. And if you balk at the epistemic implications, as, for example, I do, you're not tied to it. In this case. So this is actually a pretty good way to go. I think maybe there's some more plausible interpretations. Once we take degrees of belief into account, this kind of binary sharp lines model looks pretty okay as a model of some of the evidence that we have. So now we come to the part where I tell you why it's not okay. And it's based on other evidence. And it's other evidence that fits less well with this picture, even after you probabilize it. So the evidence I have in mind has to do with this phenomenon that's come to be called phenomenon of borderline contradictions. And these are sentences that say that something both is and isn't a certain way when it is a borderline case of being that way. Right? So if someone tells you that a color both is and isn't red, what are they trying to tell you about that color? I think the most likely thing they're trying to tell you is that the color is a borderline case of red. And this is, red's not special in that regard. This seems to happen with a range of vague predicates, and that too turns up in the experimental results. So for example, here's an old study. This was judgments about which things are near each other, whether some shapes were near each other on a slide. And these are judgments of the sentence, the circle both is and isn't near the square. With agreement expressed in a 7-point scale. So 4 here is the midpoint, and you can see there was a pair where the judgments were significantly above that midpoint. But the thing I want you to notice here is just more of the hump shape to it, right? That as we go through that middle ground, participants get more sympathetic to the claim that things both are and aren't that way. As we get towards the clear cases towards the end, they're less sympathetic to those sorts of claims. That's really the pattern that seems to have occurred in a number of experiments. So here's a different experiment done in a different way, where here participants were asked to judge sentences either true or false, or both true and false, or neither true nor false. And the sentences were something like X is tall and not tall. They're presented with pictures of people of various heights. And again, you see that same, here the responses even at their peak don't rise above the midpoint, but you still see that same hump shape, right? People are more sympathetic to these seemingly contradictory sentences in the middle ground and less sympathetic to these seemingly contradictory sentences in clear cases. Here's another sort of case or another experiment. I'll come back to this one in a bit. On these, for now, the crucial thing to pay attention to in each case is the blue lines, right? This is an experiment that's conducted in French with French speakers. But this is telling you the patch of color is yellow and not yellow, or green and not green, orange and not orange, blue and not blue, right? And those blue lines through the middle again are the judgments of these sentences reported by a range of participants. The sort of background, the S curves are the judgments respectively of it's green and it's not green. And I'll come back to how these relate, but for now, just note that hump shape in the middle. So participants do seem to prefer these sentences in the middle ground and not at the edges. And there's absolutely no way to get anything like that coming from classical probability, right? P and not P always has the truth value 0 on every line of every classical truth table. It does not matter what you multiply it by. It does not matter how many zeros you add up. You're just never going to get anything other than 0 coming out of a classical probability approach. And that is out of step with what we're actually seeing. So this has led, I'm skipping over a lot of options here. Here's one option. One thing you might do is say, look, there's not enough truth values here. We've missed some truth values in having leapt all the way from 0 to 1. And that raises the question, how many truth values are there? I like what I'm calling Biden semantics. There are at least 3. I don't know how many of you followed the 2019 lead up to the 2020 US presidential election, but one of these sort of charming young Republican fuckers pinned Biden down and asked him, how many genders are there? And Biden's response, well, there are at least 3. Which, like, for a politician, that's a really good answer. Like, go Biden. But anyway, that's my answer for truth values. I'm not actually going to fuss too much today about how many are there. Right? I need to get 0.5 in the mix, basically, and then if we can have others too, that's fine. So I'll mostly use just the 3 values, 1, 0.5, and 0 to make the point. You might also think of the interval from 0 to 1 containing all the real numbers from 0 to 1 as our set of truth values. That's also fine. That's going to turn out to work out basically the same for everything I'm doing here. In fact, all that really matters is that we contain 0.5 and that we're sort of symmetric. If we contain 0.8, we also have to contain 0.2. We contain 0.6, we also have to contain 0.4, right? That's all I'm really drawing on here is we've got 0.5 in the mix, we've got 0 and 1, and we're symmetric. But these are, I think, 2 nice ones to think of, right? The sort of simplest one and this full complete one. Those are sort of nice examples to have in mind. Here's how I'm going to handle the kind of logic part of it, right? How do truth values work on complex sentences? Well, I'm going to suppose the value of a negation is just 1 minus the value of the thing negated. And I'll take conjunction to be the minimum, disjunction to be the maximum. This is, again, there's lots of options here. This is one very standard off-the-shelf option. I think it's standard and off-the-shelf for a reason. It's lovely, it's simple, it's easy to work with. If you want to do something else, go for it. Classical valuations are just special cases here, right? We haven't removed any of our old classical valuations. If things do happen to draw sharp lines, great, more power to them. But we now have options for things to do some other things, to stop in the middle along the way. I'm going to skip an example where I just go through the calculations, yada, yada. Well, look briefly at it, right? Let A be the claim that Alice is tall, and Z is the claim that Zebra is. And suppose you have this information about their heights, right? It's some information that allows you to determine, for example, they're certainly not both tall, but it might be that Alice is tall and Zebra is a borderline case of tall, right? So that's maybe 0.2 and so on. You can see what's your degree of belief in A and Z. Ah, that's the bank name. Again, we're basically just going to multiply the truth value by the probability of that line of the truth table and just count that as a degree of belief and add it up. As I said, let's skip that. Here's a result that's comparable to the sort of result I gave you before for classical things, right? When is someone's belief state arrivable at in this way, as a weighted sum of 3 valued valuations? And this is a really lovely, interesting result that's quite recent. In particular, the 2024 paper there by Gil Sanchez et al., that's the less technical paper. 2023 is the technical paper, and 2024 is the more philosophical situating. That's one of my favorite. I think that might be my favorite paper I've read this year so far, the 2024. Highly recommend that Sanchez et al. 2024 paper. If you're interested at all in non-classical probability, check it out. It's a fun paper. But anyway, here's a key result. Lets us know how to understand, lets us know when a belief function assigning zeros and ones and numbers in between to sentences could be arrived at by doing this weighted sort of sum of 3 valued valuations. Again, we have this sort of, if B follows from A, then the belief in B must be at least as high, but now it's not follows from in classical logic, it's follows from in a different logic called S3. The only thing that's going to matter for us about S3 today is just that conjunctions do entail their conjuncts in S3. P and Q does entail P in S3. P and Q does entail Q in S3. That'll be a little bit relevant later. Nothing else about S3 matters, but if you happen to be familiar with S3, there it is. Negation has to do the right thing. The conjunction disjunction thing is exactly the same as it was in the classical case. And then there's this nifty little bottom thing, and like that, weird, and I've banged my head off that for a few weeks, and I think I'm kind of starting to see why it works. It's interesting. But anyway, the important thing is just like, we do in fact have the same kind of result very recently now about this sort of thing as we have in the classical case. So we can start to say, what sorts of belief functions would we expect to see if, in fact, people's belief functions are these weighted sums of 3 valued valuations, right? You want something like this to be able to get any predictions out. Interestingly enough, this can be extended, and this is this is probably the only original thing that I'm doing today. Is actually it's the very same belief functions are the weighted sums of the valuations that use the whole real interval from 0 to 1. There's just no change in which belief functions you get to. You can restrict yourself to 3 values. You can use the whole real interval. As I say, as long as you contain 0.5 and you're symmetric, it's exactly the same belief functions. This is part of why as I say, take the kind of Biden semantics approach, right? At least 3, and beyond that, I'm just not going to bother, is because actually, I just don't think there's much of a difference in the predictions you get at. So Paul Legray and I and some others published a paper a few years back looking at some ways in which that's true. There's nothing probabilistic there, but again, it was looking at the ways in which 3 values and continuum many values, it's kind of a difference that doesn't make much of a difference. And it turns out probabilistically, that's also the case. Sort of once you have 3, you're kind of already getting all the predictive juice that you'd get by going all the way to 0 and 1. I like 3 because 3 is simple and I get scared of large numbers. But okay, so let's get some graphs and finish up. So I'll make the assumption that the center, because now when we're thinking about someone's belief state, right, they're going to have beliefs but they're going to be distributing their beliefs over three valued valuations, right? So they're not just going to believe in sort of one sharp threshold. In some ways, they're going to believe in two sharp thresholds, right? Where the borderline starts and where the borderline ends. If we're doing it three valued, right? We've just multiplied the sharp thresholds. You want to get rid of the sharp thresholds, move to 0, 1, like the full interval, whatever. Like I said, it doesn't make a difference. So I'm going to do it the simple way, the three valued way. And that means we've got two sharp borderline. So how is someone's belief distributed over these? Well, I'll assume they're unsure about where the center is of the borderline, and they're unsure about how wide the borderline is. I'll assume those two things are independent of each other. And I'll assume they're both normally distributed, and I've just plugged in some random numbers that seem plausible to me. And here are the sorts of predictions you get about sentences like P, P, and not P, and not P. So let's look first, say, at the blue line at P, the one that starts low and then goes all the way to high. That looks something like before. Don't be misled. It's not exactly a shape that could have been arrived at before. It is slightly different in shape, but you know, as at the resolution of the experimental data we have, we're not going to be able to see the difference, I think, between that and the other sort of thing. It at least starts low, does the sort of rapid rise in the middle, and goes high, which is the sort of thing we'd expect. And again, this is now, it's not quite right, the judgment that the threshold is below here, because there isn't a the threshold anymore, right? It's a judgment where we're aggregating up, okay, before we've reached any threshold, we're not adding any zeros. Once we're considering borderline cases, we're adding just 0.5 for each of them. And then once we make it out of the borderline and into the yes, we're now adding 1 for each of them. And then all of those are weighted by all the various statistical sort of gobbledygook. And that gives us these judgments. And the green for judgments of not P, right, is the same, starts very high and then goes down. But the interesting thing and the reason to do this, I think, is what we have now for judgments of P and not P is precisely the sort of hump shape that we see in the experimental results, right? We've got people, well, not people, we've got the simulation happier with P and not P in precisely these sorts of middle ground cases than it is in the edges. And that's the finding that's been relatively robust along, as I said, I've only given you 3 studies, but like, there aren't that many studies, they all seem to find the same thing in different ways. So I think that looks pretty good. I think that's an improvement. I'm excited about that. But I want to close by doing a final tweak that I think can make it even closer to what we see in the results. And this has to do, remember I said before, don't pay too much attention to those background lines, the judgments that are just judgments of like, it is green, it is blue. Now do pay attention to those, pay attention to the relationship. So think about, for example, this first top left one, right? The color is yellow and not yellow. So as we go from, say, a yellow to a not yellow color, that one that starts high, judgments that it's yellow, and then that comes down across the middle, right? Judgments that the color is yellow are very low when the color is in fact not yellow. Similarly, low to high if we're judging that it's not yellow, but judging that it's both is that hump in the middle. Now here's the thing, that hump in the middle is for almost the entire graph higher than one or the other of the polar judgments. So what that means, for example, look on the left edge, right, where it's higher than the one that's rising. What that tells you is here's a color where on the whole, people prefer the claim the color is yellow and not yellow to the claim the color is not yellow, right? They prefer the conjunction to one of its own conjuncts. And that happens across all of these, right? Everywhere you see the blue go above any black line, which is most of the time, you're seeing people prefer a conjunction to one of its conjuncts. These are, in this case, these are forced choice judgments. They're forced just to say yes or no. Or actually, what is true and not true? True and false, Paul? Do you remember? This is stuff that Paul and I did. Do you remember what their response choices were? It was binary. Yeah, but I don't remember. Okay, and anyway, it was a binary choice, right? And so what we're looking at here is aggregates over a number of participants and a number of trial runs and so on. But again, people seem to like the conjunctions better than the conjuncts, or better than one conjunct or the other in almost all cases, and better than both conjuncts in the very middle kinds of cases. And that absolutely cannot be captured by what I've given you so far. This is where it matters, as I pointed out, that in this logic S3, conjunctions do entail their conjuncts. because there was that restriction, remember, that if we have one sentence entail another, then you cannot assign a higher probability to the premise than you do to the conclusion, right? So the pattern that we're seeing, okay, we've got the hump in play now. That's good. It's an improvement. We're getting closer, but we're still not there. And we cannot get there using the sorts of tools that I've laid out so far. So here's a plausible thought. There's been a little bit of literature on this phenomenon, because you don't have to think probabilistically. I think any way you think about this phenomenon, it's puzzling and interesting, right? That people prefer the conjunction to it, conjuncts. There aren't a lot of ways to think about this where you would have expected that. I remember that originally was found by Saint-Oxytive and Jeff Pelletier, and I remember reading that paper. Seriously? And like it's wild. No one should have expected this, I don't think. If you did, great, good on you. But I mean, it's really puzzling. And a number of people have attempted various sorts of explanations of what's going on and how this works. And most of the explanations, in fact, I think all the published ones that I've seen, they differ from each other in certain ways, but they all kind of center around the same phenomenon. And that phenomenon is when you think about a sentence like P and not P, the person is tall and not tall, the color is yellow and not yellow, whatever. In this sort of setting, that kind of can't do any better than a half, right? If the thing is yellow to degree 0.7, well, then it's not yellow to degree 0.3, and the minimum is 0.3. If its thing is yellow to degree 0.3, well, then the claim that it's not yellow is 0.7, and the minimum is 0.3. Right? You cannot get above 0.5 for these sorts of contradictory looking things. And so what at least some people have thought is like, actually, we're somehow sensitive to like, how good could this sentence have been? Right? Not how good is it absolutely, but like, how good is it relative to how good it could possibly have been? And as different people have taken account of this in different ways, but the explanations I've seen seem to kind of center around this, right? P can go all the way to truth, right? The color is blue. That could just be fully true. So our judgment of it is rated out of 1, out of that full truth. P and not P can't make it past 0.5. And so the thought is, well, what if our judgment of it is not just where is it, but where is it relative to how good it could have been? So here's a just final parting proposal that I'll make. Suppose that this effect we're looking at is a pragmatic effect. It's about what people say or what people agree to about what they're trying to indicate by what they say or they agree to. And so I want to suppose that credences, people's belief states, are exactly as I've given them to you before, right? They're the three-valued weighted sums, convex sums of three-valued valuations, no funny business, right? The credences obey all those conditions. But that when people report a sentence, so when they're forced into a choice and there's a probability of them going either way, say, here's where we scale by the maximum possible value. Right? You say, look, if a sentence could have made it all the way to true, then their probability of agreeing to it just is their belief value in it. Just is how much they believe it. But if a sentence could only make it to 0.5, then their probability of agreeing with it is just like how their belief relates to that 0.5. So if they believe it to a degree 0.3 and it can only make it to 0.5, then they're in fact 0.6 likely to assert it, because 0.3 is sort of 0.6 of the way to 0.5. If I did the numbers right. Now, if you suppose that, and like this is, I'm not doing a ton to motivate it here, right? I'm just sort of saying like, let's see what happens if we think something in this area. I think it seems not completely. I could have come up with something less plausible, let me put it that way. But like, it's not super unmotivated. But then what you actually get looks a ton like the experimental data that we've got across these things, right? You get it coming up basically as soon as you can see it starting to come up. It peaks roughly around, it doesn't go all the way to 1, right? You get this nice little peak in the middle, and you start to see, okay, I think we're getting something here that actually potentially gives us a grip on what we're seeing people do in these experimental situations. So at the moment, that's not much of an argument beyond like, look, these pictures look similar, right? Which is not a great argument. I'm fully aware of that. But I think this is sort of where you start, or where I'm starting, in trying to develop a formal theory that will hopefully be able to become one that gives us some kind of predictive or explanatory grip on what we're seeing people do in the lab. Because what we're seeing people do in the lab is really weird. And so I think it's worth developing theories that start to exhibit that sort of flavor of behavior. So here's how I'm going to sum it up. Sharp binary theory of vagueness can actually be made okay when you go probabilistic with it. It's not as bad as it would seem, and probabilities, I think, are pretty key to making it decent. But it's just okay. Right, there's absolutely nothing in that approach that gives us any kind of traction on borderline contradiction. If we add some more truth values into the mix, the same kind of probabilizing just works better. You just start to get these humps appear exactly where they do appear in real judgments. Still some trouble with what I'm calling the Anxiotif-Pelletier effect, that last little bit about getting the hump to come up over the individual lines. Less certain about that, but a very simple-minded kind of pragmatic overlay seems to look decent. But even if that's wrong, I think the sort of probabilizing, the more many-valued stuff seems to be on the right track anyway. So yeah, thanks very much. That's the status report.